Hello, another problem. It has to do with your Gaussian surface. And in this particular problem, we're going to be talking about the conducting sphere. So a hollow conducting sphere with an outer radius of 0.250 n and an inner radius of 0.2 m is a uniform surface charge density of plus 6.37 times 10 raised to negative 6 coulomb per square meter. A charge of negative 0.5 microcoulomb is now introduced into the cavity inside the sphere. The first one we need to take note of is what's the new charge density on the outside of the sphere? We're looking for the new charge density. And you do remember we've got three: linear, surface, and volume. So this is a conducting sphere. It's not linear. So you've got to know if you're going to be making use of your surface charge density or volume charge density. So it's either sigma or your rho. Now, after which we can calculate the strength of the electric field just outside the sphere and also the electric flux through a spherical surface just inside the inner surface of the sphere. So let us use three different boards for the three different parts of the problem. Okay, let's have the given here. Okay, we've got a given of outer radius. Let me have outer radius is equal to 0.250 m, it's an m, and the inner radius is 0.200 m. Okay, right. Surface charge density, uniform surface charge density. So this is surface uniform is 6.37 times 10 raised to negative 6 c over m squared. As you see, it's a charge per area. So this is, it has to do with surface and not with volume. Now a charge I would like to use Q naught because this is the charge that we just introduced. That is negative 0.5 microcoulomb. Now introduced into the cavity inside the sphere. So let's see it. Letter A, what's the new charge density on the outside of the sphere? So we're looking for the outside of the sphere. This is the new one. Okay, let's focus on this first. Think of an equation wherein we could use or we could see surface charge density. One of the equations that we could use is your electric field is equal to your surface is your charge divided by your epsilon naught. This is actually quite similar to your electric flux is equal to enclosed charge divided by your epsilon naught. So if I were to rewrite it in some way, that would be your electric field is equal to 1 over 4 pi epsilon naught, multiply it to the charge divided by your r squared. And given that I can make use of these two equations to understand or to know the surface charge density of the outer sphere. So manipulating this, I can get E multiplied to your epsilon naught. That's for your surface charge density. So the E there, I can use the second equation. So first and second equation. Back here, that would be your surface charge density, then this is your E, 1 over 4 pi epsilon. You can use K here. In some literature, they just use K, which is 9 times 10 raised to the 9th. And then that would be Q divided by R squared. That's your E. Multiply it to your epsilon naught. Now, I can see that we can try and simplify it even further. Got to my 1. So let's have it in one system. Q 4 pi epsilon naught r squared and my epsilon naught is just multiplied there. I can see canceling out, and then I'll just have Q divided by 4 pi r squared. Now, Q divided by 4 pi r squared, we do have our value, so just plug in. Your Q in this case is negative 0.5. This is micro, not nano, so that's times 10 raised to negative 6 coulomb. Divided by your 4 pi. Pi is constant. Why did I stutter there? R squared. Which part here? So you have to know if it's the 0.250 or 0.200. We're looking for the surface charge density outside. So we are going to be using the radius outside. That's 0.250 m squared. Make sure that you've got it in m, so you don't need to convert it anymore. So this would be negative 6.37. 6.37 times 10 raised to negative 7. This is coulomb per square meter. Should really parallel or consistent to the knowledge that we've already learned before, like surface charge density must be charge per your area, so C per square meter. All right, and the next question is basically letter B, calculate the strength of the electric field just outside the sphere. So same thing. The electric field just outside the sphere. How do we deal with this one? A while ago we had E is equal to your charge density divided by your epsilon naught. So might as well make use of that here. E equals sigma divided by your epsilon naught. Sigma in this case, or 6.37. I'm going to be making use of that because that is our uniform surface charge density. 6.37 negative 6. It's 10 raised to negative 60. Divided by your epsilon naught, which is 8.85 times 10 to 12, c squared and m squared. Okay, that will give us a value of 8.85, 6.48 times 10 raised to 5. This is 5. This is electric field, and obviously, yes. Okay, so this is 6.48 times 10 raised to 5 and let's see. What about our letter C? Question is, what is electric flux through a spherical surface just inside your inner surface of the sphere? What is the electric flux? What is the electric flux just inside the inner surface? So that would be still Q enclosed divided by your epsilon naught. Your Q enclosed here, your Q enclosed, it's inside, and we know that your the charge, we named it Q naught, is equal to negative 0.5 microcoulomb. That is the one inside the sphere that's that was put into the cavity. So we're going to be making use of that one. That is negative 0. Micro, so that's negative 6, divided by your 8.85 times 10 raised to negative 12, excuse me, C squared and M squared. Okay, that'll give us some negative 5.647 times 10 raised and M squared over C. is it? Now, the electric flux inside the surface where we introduced your Q is equal to negative zero point 0.5 microcoulomb is calculated as negative 5.647 times 10 raised to 4 Newton meters squared per coulomb.